All right, folks, this is a second recording of our lecture for the evening. The audio stopped working in my first recording during class, so I will run through the material again. It will be a little quicker, but hopefully I'll still be able to cover the questions that were asked during class, just so they're recorded on the audio, and you'll still get all the material. So first we went over the homework, and I will show you the output of the homework. And the key here, there were a few changes. So for each of these classes, I had to set a variable inside the class. I set private variables. I named them all with an underscore just to keep them different from the parameter names. So I set that private variable on the constructor, which wasn't done in the example or in the framework. I updated the math for each of them. So here, two variables, height and width, different formulas for each object based on, your ninth grade geometry. Circle has a radius, 2 pi r for the perimeter, pi r squared for the area. And then the big key was adding virtual, adding the word virtual to the functions at the shape class. And if you didn't have those virtual functions, even if you implemented everything right, you would still get an output that had negative ones. Because our variable at the bottom, the reference to them, the variable type, is always a shape. So since it's not a virtual function right now, the get perimeter length and the get area function are called with a reference to the shape class. So it always calls the shape implementation of these functions. So when we call them virtual functions, like we talked about in week 10, I run the code again. And now the execution environment knows what the reference is to what the actual object reference is, even if it's a shape pointer, even if it's a shape pointer, because it's a virtual function, it looks to see that it's actually a circle or actually a square or a rectangle and calls the proper function. So those are the changes for the homework. All right, that was it. So in today's slides, we're going to talk about recursion. Recursion in chapter 7 of your book, page 153. Recursion is the process of defining something in terms of itself, circular definitions. I spelled something wrong, but whatever. I'll change it. So here's a quick circular definition. A circle is defined as something circular in shape. So the problem is you have to know the definition of circular to be able to know what this definition means, but the definition of circular is a definition of circular. So it's kind of this like recursive definition. So in programming, not just C++, recursion is the process of a function calling itself. So it's a function that calls itself is said to be a recursive function. We're going to go through a couple of examples. And since I'm doing this lecture for the second time, I'm going to go and do the easier example first. So let's go to a string reverse function. I think this one's easier. So if you don't, then skip to the factorial and then come back to the string example. But I think this one's a simpler example. So what this function does is it prints out a string in reverse. So the string is a character array, which we know this is a test. And we know that there is a null terminating character or a zero, like an integer 0, that's added at the end of this character array. So the reverse function takes a pointer to a character. So in this case, it's a character array. I'm going to print out the word reversed, call the reverse function, and then print a new line. Whoops, I always do that. So the reverse function itself, it says something tricky here. So it says if star s. Let me get to my actual code environment. This will make sense. So if star s. So what this is doing, it's dereferencing the pointer to a single character. So think about we're at a character array. I always draw them left to right, right? So on the left side, you have a T. On the right side, you have the 0. So when we dereference this for the first time, we're looking at that t. So if t, so if not 0, right, if it's not that null terminating character, I'm going to call the reverse function again, but with the next character as the focus of this variable. So if the first word is this, the first time I'm looking at the t. Then I'm going to call the function again looking at the h. And the logic says if not, if it's true, if it is a positive value, or if it's a non-zero value, an h, I'm going to call the reverse function again with the next one. So what I'm doing is building this stack. So in the machine, it's an actual stack data structure, which we talked about before. The coins in your coin slot. So the first thing I put in my stack is a t. The next thing I put in my stack is the s. The h. The next thing I put in my stack is the I, then an s, then a space, then a e. The whole way until I get to that null terminating character. The null terminating character will evaluate to false, a 0. So that's where I have this else block, which is super critical when you're building this recursive function call. You need a time when you exit out of that function, that loop almost. It's not a loop, but it's almost a loop. So when you want to finish your recursion, you always have to have that case where you leave, where you start returning data, not just calling the function again. You can think of it like avoiding an infinite loop. The problem you'll see is you'll hit what's called you'll overflow your stack. So you'll put too much data on a stack, and your operating system will kill your program. So here you'll see when we're at the end, we're going to return. We're just straight up returning. Then you think about, we start coming down that stack. Since I've already called my reverse function, the code comes back into the calling version of the function, and it's going to print out that character. So remember, we've moved to the right in that array or up of the stack. So it's going to point out the last thing first, the t. Then it's going to come down the stack again and print the s, the e, the t. So it's going to print it out backwards. So when I run this program, you'll see it's going to print out the string backwards. In class, I talked about this not really a reversing function because it's not really like changing the string itself. It's not changing the value in the array. It's just printing it out in a reverse. So it's a pretty simple way of looking at this recursiveness of the function. But again, the tricks are dereferencing the pointer to be a specific character that we're looking at. And then we're going to move the pointer up or to the right on the array by increasing to point to the next character. It's called pointer math. We're adding 1 to the memory location because the pointer is a memory location. Say it's memory 412. I'm going to now pass memory location 413, then 414, until I get to that 0, that null terminating character at the end. Then I start coming out of my program. All right, so that is the string reverse function. I'm going to go back to factorial. I have another typo on one of these pages around here. Yep, classic. The classic factorial example. So factorial of a number. It's a math thing you probably learned at one point in time, but you're multiplying a number by every number between 1 and that number. So if we're calculating factorial of 4, we're going to calculate 1 times 2 times 3 times 4. Calculating factorial 6, 1 times 2 times 3 times 4 times 5 times 6. So I'm going to write this in two ways. I'm going to write it in an iterative fashion, which is just building a loop to do that. And then I'm going to write it in a recursive fashion. So if we look at the iterative implementation, again, I'll jump over to my code. I'm defining a factorial function, fact. I am going to call fact 9 times, starting at the number 1 up through the number 9, less than 10. And I'm just going to print out what that number factorial is. So the first one I'll print out 1 factorial is whatever it returns. 2 factorial is whatever it returns. So the factorial function here takes in that number, starts a counter, keeps a value for answer in memory, and then starting at 1 until we are up to the number less than or equal to that input number. So if it's 5, we're going to count from 1 to 5, inclusive, counter plus plus on every loop. And here we're going to set answer to the previous answer times counter. So we start at 1. So the first time we hit counter, counter is 1 times 1, answer is 1. So now answer is 1, counter becomes 2. Answer is 1, answer is 1, times 2 is 2, so answer becomes 2. 2 times 3 becomes 6, etc. So we're gonna continue to multiply cumulatively on this answer. So if I run this, you'll see our output is factorial 1 is 1, 2 is 2, 3 is 6, etc. So we're calculating the factorial. So now let's look at the recursive factorial. So here we have another function, looks similar, but I added the letter R to signify recursive. So factor or factor int n, same look, same loop. I'm going to call my recursive factorial is, and I'm going to output the value, and same interface here. But here's where I'm going to do something a little differently. So remember our incoming number is, the first time we call this function is the maximum number. So let's say it's 9. Answer again is going to be where we're going to hold the return value. If n equals 1, we're going to return 1. So this, you think about this, that's the termination state. If n doesn't equal 1, we're going to call factor again, passing in n minus 1. So the first time we're going to pass in 8. Then going through the logic again, we'll call factor r with 7. Then 6 times, then 5, 4, 3, 2, 1, until it gets to that end state of 1, where it returns 1. So then we have 1 times the previous number, which is 2, times 3, times 4. So I tried to build this visual down here. So the first time we call factorial with 9, and so I'm building a stack. So I'm starting at the bottom. In class, I built this from the bottom up. So factorial 9 calls factor with 9 minus 1, which is factor with 8, which calls with 8 minus 1 to get 7, which calls with 7 minus 1 to get 6, etc., until factor r with 2, calls factor again, passing in 1 because we've subtracted 1 every time. And then we get to the top of this stack where factor is 1. We're going to start coming down or unrolling that stack. So I take the 1, I return 1. And here is the right-hand side of that equation. So I'm showing the recursive call times what was passed into it plus 1. What was the original value? So we have 2 times this returned 1. So now I have 2 times 1 is 2, which gets returned ... to come down to start accumulating at the bottom of our function. So if I run the recursive factorial, I should get the same output. And I did. But it just it calculates it in a different way. All right, and so that was how we ran it fact recursively. Both these code links are there. I kind of broke it down one by one, but we start at the function definition, factor r. Fact r takes the n value, stores an answer variable, returns on 1. This is critical. Just like a loop, you need to break out of your loop. You need to break out of your recursiveness. For this function, we're calling factor again with n minus 1. And whatever that returns, we're going to multiply by n. This is how we're going to start at 9 and multiply it by 8, by 7, by 6, by 5, 4, etc., down to 1. There are certain data structures that almost require a recursive implementation of some functions. So there's a concept of a tree structure where we have nodes that reference other nodes. So one of the students in the class tonight came up with this Jamboard drawing of this node structure. Thank you very much. So if we think about, we'll start building this, but here's the idea. If we have one node at the top, this sticky node is a node. It points to a left and a right node. It has a reference to two other nodes. And since it's another node, it has a reference to a left and a right node. So if we think about that recursive process, say we wanted to find a value in a node. We wanted to see if this tree structure had the value 15 in it. We'd say, okay, does this 0 have a, and if we had a find function, does this node have a 15? Nope. Call the find function on my left node? Nope. Call the function on my left node? Nope. Call the function on my right node? Nope. And so we have this recursive implementation of a find type function. But here we're going to build a class. We're going to have a left and a right private variable, which are other nodes. And we'll have two functions, add and print. So here's a quick implementation of a binary tree. Binary is for two, binary 1 or 0. It's two values. Binary for two because that is a reference to two other nodes, a left and a right node. And then we have an integer data variable to store what the data, what the value of that single node is. We have two constructors. One has no parameters, and we set the data value to 0. We also initialize the left and the right node references to 0, effectively to null. Our other constructor, we have a integer v variable as a parameter to our constructor, where we set the data value to v. Again, left and right node, we set to null. Then we're defining the prototypes of the add and the print function, which we will implement here. So in our node add function, we see the parameter is a pointer to another node. So when we're adding this structure, so if you think about, we built a root node using that constructor where we can set a default value. We've added this root node, and that root node starts with no reference in the left or right value. So if there's no left pointer, we set left to this new node. If there was a left node, then we set, and there's not a right node, we set the right node to whatever this new value is. And then we have a little bit of logic here. This is not a great binary tree implementation. It's not going to come up with like a really nice balanced binary tree, but for sake of class, we'll just go through this implementation. So if the new node's data value is less than the left node's data, then we will add the new node to the left node. This is where this function becomes recursive. Otherwise, we will add it to the right node. So if the new data was greater than or equal to the left node data, then we will add it to the right node. So you can think we kind of add to the left, then we add to the right, then we do a little bit of comparison and end up adding it again to the left, which might end up adding it to its left in this recursive manner. Then we'll do some quick printing. We have a print function which says if I have a left node, I'll print out the left node by calling its print function, which might in turn have a left node, which would call its print function. So again, we're building this recursive function here. After that's, we're building up another stack potentially, which when it unrolls the whole way, then we'll print out our value, the node that we're referencing here's value, data. Then we'll print out the right node. So here's a little bit of code to create this structure. So we start with a root node. We'll call it root. That's a very common name for calling the base or the root of your tree. Then we'll add a node 1, we'll add a node 2, -1 and 12. And then we'll end up printing it. And let me show you a couple of examples of what that printing looked like. I already covered here what there are two recursive functions, the add and the print, because add called add. It was a different node reference, but it was still calling the add function. And then same with print. It was another recursive function because it called print just with a different node reference. And this is where you will, in programming or in software development, this tree structure, like this recursive structure of data, Whether it's a tree, whether it's a linked list, which would basically be a node with a link to another node, which would have a link to another node. They're really hard to build iteratively, especially with a tree, because it's got the left and the right. It's easier to build a linked list iterative function, but with trees it's really, really hard. So you'll naturally come to these recursive functions. So let's run that code real quick a couple times. Whoops, that's a zoom. Let's go to Visual Studio Code, and we'll go to our binary tree program. I changed it up a little bit here. I added another function to visualize it a little differently, which I'll show you. But for right now, I'm changing the values of 0, 20, 10, 30, 5, and 15, which goes back to this drawing: 0, 20, 10, 5, 15, 30. So when I run this, you'll see it does something a little funny as far as the printing goes. But if you think about how the tree structures itself, first it recursively calls the print down the left. So it prints down the left side, then prints itself, and then prints the right side. So let's see if I can get both of these together, which I didn't do during class. So here you have an advantage. So we start with this reference to our root node, or 0. So if left, print left. So it has left, print left. So now think again, we're at the beginning of this function again. Up the stack. So it says, okay, do I have a left? Then I'm going to print left. Then we're down on this. Oh, you can't see my mouse maybe. So root node left is 20. 20's left is 5. 5 doesn't have a left, and so it's going to print data. And that's why you'll see 5 first. And then 5 says, do I have a right? No, it does not. So we go back up the stack to 20 again, and that's why you'll see 20 gets printed out here, because we finished printing down the left. Now we print 20 self, and now we go down 20's right, and you'll see 15. So now we're referencing 15. 15 doesn't have a left. I'm sorry. We're referencing 15. 15 doesn't have a left. Then 15 prints itself. 15 doesn't have a right. So it goes back up the stack. So when we're referencing 20, we're done. So now we go back up the stack to 0. And that's why we print 0 in the middle here, because we printed down the left, down its left, and come back up the stack. Now we print 0 from the 0 node, and now we go down the right. So we get down the right node to 10. Well, then 10, if we're in the print function for 10, 10 has a left. So it calls the print function on 30 node. 30 doesn't have a left. 30 prints its own data. That's why you'll see 30 here. 30 doesn't have a right, so it returns. 10 prints its own data, doesn't have a right, and returns. So that's why it printed out in this order. I added another quick function in here, trying to print it in a more visual way. A quick binary tree printing I found online. The node binary tree structure is so common, like I copied and pasted the code and it just worked. But so it's this print 2D function. So I will compile again and execute again, and you'll see this output down here. So if we kind of tilt our head to the left, 0 is our root node, right? Or correct. Then 20 is left, 10 is right, 10's left is 30, 20's left is 5, 20's right is 15. So it's kind of this Jamboard picture, but tilted to the side. So one of the things I like to do when it comes to data structures like this is just figure out a way to visualize it. I've been doing this long enough where I can visualize a binary tree in my head pretty darn easily. Because all it is, it's a node with a reference to 2 other nodes, which might have references to 2 other nodes. So that kind of visualization helps me figure out algorithms and figure out how to code this stuff. I know I'm going quick. I'm going a lot quicker than I did during class. But I think I'm trying to cover all the questions that we had in class too. So the second topic for the night is file I/O. And next week, we're going to build these two concepts together. We're going to build on top of each other. But for right now, I just want to run through file I/O super quickly. The C++ I/O system, or input-output, that's what I/O stands for, can perform operations on files on a file system, or more accurately, file type things. But think about it like files on a file system. So if we're in our file system, I just typed ls to show all the files in my file system. So I'm going to remove this test file, and we don't have a test file right now. Okay, cool, because our code's about to create one. There's the concept of a stream, an input stream, an output stream, or a stream that can be both input and output, because it does not just have to be a file. But for files, you typically read a file or write to a file. Okay. So the steps to do this are to create the stream and open a file. So you open what's called a file handle. So you open a reference to a file on the file system. Then you interact with the file. You read or write from that file. Then you close the file. Closing a file is super duper important. If you don't close a file on a long running program, you could eventually create and open, hundreds or millions of files, and your operating system will kill your program, or you'll crash your operating system, and it's really bad when that happens. So always close the file, super important. So here's a quick example of how we can write to a file. We're using a new library called fstream for file streams. And here's the code in our main function. We are creating an OF stream, so an output stream variable called out. And we are passing the word test to the constructor. So we are creating a file called out. The next line is important. So consider the out variable. If the application is unable to open the file, out becomes null or 0, right? So if not 0, which is inverting, so if this is the same thing as saying if out is null, then we're just going to print something like, we're going to handle the error. We're going to say we cannot open the file. Then we're going to return. But if we do, then here I'm going to do a simple output of data to that output handle, using like the construct we did with cout or count. We're going to pass in the number 10 space the number 123.23 and then end line. Then we're going to print out a string saying this is a short text file and the end line. We are opening this file without any extra parameters. So we are opening it as a text file. There are other parameters you can say to open it as a binary file, etc. If you want to store images or something like that. But for right now, we're just doing text. So after I output that data, I close the file because closing files is super important. And then I return 0, indicating successful execution of my program. So let's run that code now. So I have my write.cpp file. We'll compile it. And we will execute it. And nothing happened on our screen, which is right. So I'm going to output, I'm going to print using the cat command that file. And you will see the text that we put into the file comes out 10, 123.23, new line. This is a short text file. Awesome. Clear that. Go back to our code. So now we want to read that file. So again, we'll use the fstream library. I'm going to create some variables that I'm going to bring data from that file into. Here we will ifstream, ifstream input file stream. Again, we'll name it in, and we'll pass a string for the file name. So here we've created we're opening to read that test file. Same thing, if we're unable to open it, we will print out cannot open file, and we'll return 1, indicating an error because it's a non-zero return value. And then, like we use the CIN or the SYN functions or syntax, we'll use in, and then we'll read an integer, a float, a character, and a string. And then I'm going to cout. I'm going to print to the console those values that I read in. So let's run this code twice. So I'm going to remove that test file first to show you what happens if you can't open the file. So I will read and execute. Cannot open file because there is no test file. So it is not creating the test file when I'm trying to read it, but it does create the test file when I try to write to it. So let's run that write program again. Now we have a test file. Now we'll run our read program again. And I printed out what I read from it. So now remember, there are some weird things that happen when we use this syntax for the count and the CIN that apply here as well. So when there are spaces, it counts it as end of the input and stuff. So the non-printable character down here is kind of weird, but that's okay for right now. We'll get into better ways to open and handle file data, like we got into better ways of using of reading user input. But we'll get to that. All right. So the homework for this week is pretty straightforward. Nothing recursive yet, which I didn't say in class. I'm curious if anyone's going to write this recursively. That'd be kind of fun. Write a program that generates a list of 1,000 random integers. And, ooh, my word count's wrong. But anyway, write a program that generates a list of 1,000 random integers and writes them to a file. Each integer must match between -10,000 or must be between -10,000 and 10,000, exclusive. So no 10,000 and no -10,000. There's a rand function that you can use. I linked to the documentation. I hope you can figure out how to use it. Your program should require no user input and should not print anything to the standard out. So no count, no printf, etc. Your program must write to a file called randoms.txt. Each line must only contain an integer and a new line. If you run word count -L on a Mac or Unix system, the output should be word count -L randoms, and I will change this to be 1,000 randoms.txt, not 10,000, 1,000, as I said at the top, 1,000. The Windows equivalent of that word count program might be this. I don't know. I don't run Windows, so I can't really tell. But I think it is that. This is due Wednesday, April 15th by midnight. Your file name in GitHub must be your repository week 11 random_write.cpp. Ignore that. That was from last week. Copy and paste. Didn't delete it. Email me when you're done. I like that habit. That way I know when you're done. This homework is critical for next week's homework. So make sure you get it right. Email me if you have any questions. I think that's it. Thank you for a successful class.